Hello. So hopefully you will enjoy this. Okay, so we would like to talk about malware development, quite an interesting topic we've been recently browsing with Pavel. So let us start with introduction. Can we change slides here? Okay. So my name is Patryk Czeczko. I currently work at this Purple team in Standard Chartered Bank. Previously, I worked at Deloitte, at the Red Team Deloitte, together with Pavel. And
Yes, my
that's my short
name.
story.
Yeah, my name is Pawel Kordos. I work as a penetration tester in K&D, and previously we've been working with Patryk in Red Team Deloitte. I was a senior consultant here. We've done a couple of interesting engagements. We've gained some knowledge, and we'd like to share it with you today.
Yes, that's it. So, about this presentation, we are going to focus on malicious code development and mainly on Windows platforms, because during red teaming engagements we usually post-exploit Windows environments, Active Directory domain, so that's our main area of interest. And we are using C++ because it gives us direct access to Windows APIs, and it's harder to reverse than, for example, PowerShell script or .NET application. So we're sticking with pure C++ or C. Um, we will talk about bypassing modern defenses like antiviruses, EDRs, or sandboxes, virtualized environments, but also some techniques to make malware analysis harder, to obfuscate code, hinder debugging, and also few words about hiding malicious code in legitimate apps. So this includes both code injection and backdooring. So Pavel will tell more about backdoors later. So let me start with basic information on how detection mechanisms work now. So we can say we have three types of detections. First one is basic signature-based detection. So files are analyzed for checksums, for known strings, characters inside the executable, for example, and known byte sequences associated with some malicious opcodes, malicious assembly instructions, for example. Then we have heuristic detection. So it's basically an analysis of application behavior. It can be, for example, based on import table in Windows executables. So antivirus can analyze, or analyst can analyze the file to understand what action is it going to perform on the system based on functions it's importing from the system, from Windows DLLs, for example. And the third kind is sandboxing, which is dynamic analysis when the sample is executed, or as it's called, detonated in a controlled environment. And as the application is executed, it's analyzed by this, for example, the sandbox to see exactly what is it performing during runtime, and actions are monitored to better understand this malicious application. So how are we going to fight those detections? So for a signature-based detection, we can simplest thing to do is to recompile the executable. That's how we can get a different checksum each time. So we find this very basic IOC, which is MD5 or SHA signature. We can also do something more difficult and a little bit sophisticated, which is polymorphism. So it's basically the code that modifies itself. It's maybe quite easy to add some garbage data to an executable every time it's run, so the checksum is changed. Resources encryption is valid for signature-based detection and heuristic detection, so it's commonly used in malware malicious code. So any data stored in the executable, like strings, configurations, and so it's executed and it's encrypted, and it's only decrypted during runtime. So for heuristic detection, for combating those detections, we can also implement some code obfuscation. For example, low-level virtual machine obfuscation or anything else that makes the code harder to analyze. Dynamic code, which means like loading functions during runtime and maybe changing the code using reflection on shellcode level. And for sandboxing, we can use simple environment checks and ifs. For example, if the machine the sample is executed on is constrained with resources, for example, it has only 1 or 2 gigabytes of RAM, it's probably some sandbox, and we can terminate our process here. So starting with the basics, we have like this malware primitive, which is a shellcode. And what is a shellcode? Shellcode is some kind of position-independent code, which, for example, may be injected during binary exploitation of an application or injected in some process. And it usually bootstraps itself to find specific memory structures and functions in memory and use those functions, for example, to open a bind shell or reverse shell or anything. Shellcode by design contains some clever features which we will discuss briefly. And shellcodes are like ultimate reflective code because it can change itself very easily. So that's why there are a lot of, for example, those simple XOR encryptors that the shellcode that decrypts itself on the runtime and then executes. So it's some anti-analysis mechanism implemented in shellcode usually. So how Windows shellcode works? First, process environment block is located in memory. It's quite easy to locate it. Then process environment block has the links to loader data, which has information about loaded modules. And I guess every application has those Windows libraries loaded at runtime, like kernel 32 or RTDLL, and we can browse those libraries in memory to find the functions that we need, and mainly these are get pros address and get module handle and load library. And which shellcode can use those specific functions to find any other function, for example, load socket library and call functions to, in this example, create process and assign the standard input and output to create socket. So it's a basic, very basic reverse shell, for example, generated by Metasploit. And here is example of basic injection. For example, when we implement some loader in C++, which injects our shellcode, wherever it is, for example, Cobalt Strike shellcode or shellcode from any command and control tool or whatever. The basic technique is to allocate virtual memory in the process and then create a new thread. And note a few things here that when data execution prevention is enabled, which is common nowadays, we need to give proper permissions to the memory. So this second code snippet, like casting shellcode to function pointer and executing it, won't work because we need to have memory with read-write permissions, as you can see on the second line of code. So it's a very rudimentary technique of injection, but sometimes it's used. Okay, so we have this basic proof of concept, which injects our Metasploit shellcode in the process. Let's test it against VirusTotal. So after uploading the raw shellcode, we get such detection, like 23 or 50, and this injector compiled in a C application is also pretty much detected by antiviruses. And we can implement some very basic things here to hinder the analysis on VirusTotal to obfuscate the code a little bit. So first thing is XOR encryption. Very simple. We just XOR every byte with some value. Then great thing to do is to create some fake, just some software certificate and use it to sign. It don't need to be in any certificate path, just any code signing certificate will do here, and we can drop the detection rate when the executable is signed. And other thing is to switch to x64 architecture and using those three very basic techniques. So in XOR encryption, code signing certificate, and x64-bit architecture allowed us to drop the detection rate to only 3 from 20 something that was before.
Yeah, all right. And now we'd like to focus more about the anti-VM solutions, because the two main threats which we will be actually fighting in our development is, first, this is antivirus solution, but probably you would like not to get catched so easy. So he also has to face malware analysts, which probably will receive our malware for further analysis. And we'd like also to make some security measures against them. As the first step, both sandboxes and analyst virtualizes OS usually can't 100% emulate the actual execution machine like a workstation. And they usually are simplified machines with limited resources. And there are some other things which may be our indicators to verify whether we are facing a virtual machine or a physical one, like, for example, device name or some USB information. Also, MAC address of the network card is useful here. And let's go through a couple of these. So, as I told, the first thing are the limited resources. Sandboxes may not be able to 100% simulate the physical machine. Therefore, we can simply check the number of processor cores on the system. Maybe not most, some of the AV products cannot afford allocating too much resource from a host computer in order not to slow it down too much. So we can first check how much core is on the machine we are currently running, and if less than, for example, 2, we can shut our program. Second is check the amount of the memory system. Same story as before. Sandboxes cannot allocate too much memory, and we can check how much memory is available on the production system. In this particular example, we are assuming that a minimum of 2 gigs of RAM will be on our target, but we can modify that if we know that, for example, this company is using machines like a developer unit with 32 gigs. We can increase that. So if it's less, our program will not run, and I assume that none of the antivirus solution or the malware analyst will have such a big amount of memory shared with the virtual machine. Other things which we can do, we can make a huge memory allocation. This one is pretty much just like 10 gigs, probably too much, because it may actually crash on a target machine. But we can try to allocate, around 1 gig of RAM. So antivirus probably will not be able to run to allocate that much of memory for obvious reasons. So we can do that. Then we can free this memory. And one interesting trick to fool the machine is to try to load a library. So loading a library may be useful, but try to load a library called, for example, fake DLL. And probably fake DLL would not exist on our target machine, and this is what we actually will suspect. And normally, when we try to load a non-existing DLL, the function should return null. But some dynamic analysis mechanism in antivirus solutions allows such cases in order to further investigate the execution of the flow. So we can make use of that and try to load an existing DLL. The next thing, which Patryk previously mentioned, is multi-threading. So automated analysis is performed in a simplified sandbox environment, and sometimes it may not be able to enumerate of the nuances of the real environment, such as, for example, multi-threading. And it's always harder to reverse engineer a multi-threaded portable this file, and it's also challenging for an AV product. So this multi-threading approach can be used with all of the other execution methods. So we will just create a new thread with our shellcode. And I've mentioned before that virtual machine can be spotted because they make use of similar computer names and such a thing like this. So we can also check the computer name. Probably your workstation in a corporate environment would not be called admin or a desktop. This pattern actually differs for a different engagement. If we have a knowledge of a target environment, we can, for example, try if the computer actually matches our pattern. But if not, we can just try to avoid machines like admin or desktop. So if it matches this pattern, our malware will simply not run. And we can also check the username, because probably most of you do not work on a username, on an account with a username admin or user, and some of the antivirus solutions, they just simulate things like this. So we can check that. And since we will be targeting a corporate environment, we can assume that the computer is actually a member of a domain. So we can check the domain membership status. And if the computer which runs the malware is not a member of the domain, our malware will simply not run. I assume that most of the malware analysis have the lab, but for sure not always they run our malware in a domain environment. So we can also make use of that. Some of the environments which are used by both sandboxes and for malware analysis purposes, they are usually a fresh Windows installation, or at least looks like a fresh installation. And they may lack some artifacts that appear over time on a typical workstation. So one of the good examples in this is the number of USB storage devices mounted in the system, which is stored in the registry, so we can check if a user USB device has ever been mounted on the system. And it will probably give us some interesting knowledge whether this machine has actually been used in a reality or not. There are also some other artifacts which are typical for the virtual machine, like, for example, VirtualBox guest additions or some registry entries. And we probably would like to check that and verify whether we are facing a virtual machine or a physical device. So on a physical device, you probably will not have the regular VirtualBox and other guest additions. We can also check if some of the programs are running on a machine. So, for example, a regular user, such a corporate worker, would not make use of Wireshark on its device. So that may be actually a good indicator for us whether to verify if we are facing a real machine. And usually, when it comes to the network devices for any virtual machine, they have to be simulated for most of the cases, of course. And especially, you should pay attention to those network devices, because as probably most of you know, the MAC address can indicate the presence of a virtual environment, since the first 3 bytes of the MAC address are actually a manufacturer identification number. So we can alliterate all of the available network devices and compare those first bytes with well-known values. Of course, you can also simulate that, but it works for some of the antivirus solutions, and probably vast majority of malware analysts won't make use of a real MAC address. And we would like also to focus on some anti-debugging features, because our malware may be then debugged, and there are some specific characteristics indicating that the application is being manually inspected by a malware analyst. And we can then set some traps and make it harder for analysts to reverse our code. So first thing we want to do is probably to check if the application is executed with a debugger attached. So there's a simple function, is debugger present, so we can just check that. And there are some other specific flags, for example, set in the process header space when it's being debugged, like anti-global flag. It's a collection of flags located in the PEB, which may indicate debugger presence. Of course, there are a couple more debugging technique. Those are just two of this, but it mostly depends on what kind of software you are actually facing. And one more tip: if you try to place such a trap in your code, just make sure that you are not actually trapping for you. So if you are using, for example, Virtual Studio Debugger, try not to bypass this debugger, because you may have some problems with debugging your own code. And we've done some basic steps, and those are the actual steps and done in a piece of the shellcode Patryk presented before. And I think that this may be enough. And let's check if it actually did something to our code. And was it magic? No, it's a score on this malware .executable file, and it actually wasn't detected on the VirusTotal. Well, VirusTotal is not a perfect solution, because even though there are some sandboxes inside of it, those are the simplified sandboxes of a simplified environment. So probably this is not 100% sure. But anyway, we tricked the VirusTotal. We've got 0 score, so our malware is a definitely legitimate file, and to recommend to open in a real environment. And there's one big thing regarding the evading of the antivirus solution. As usual, the most valuable thing in the world is the time. So it is in a malware development. So the clock is ticking, and Patryk.
Okay, so there's the thing with delaying execution, because, for example, to evade the sandbox analysis, we could just sleep our application for a few minutes. But sandboxes are wise now, and they can just fast forward those sleeps by hooking Windows API functions. So here you see the execution flow of sleeping. Finally, and delay execution syscalls is called, and it can be this anti-delay execution function can be hooked by some EDR or on Cuckoo Sandbox, whatever, and some long sleeps called by us on the code can be bypassed simply, fast forwarded by analysis environment, and it may not be that easy to actually delay our code execution for a few minutes, and we can use sleep or anti-delay execution function, but it may both be hooked. And what we can do to avoid this detection is to, for example, use get tick count function, which gives us time in processor ticks, or 100 nanoseconds intervals from when the computer was started. But this function also could be hooked. But there is some cool thing which is kernel user shared data, and it's some read-only data available from userland, and on specific offsets it stores this tick count, and we can, for example, read the time from there. So, for example, when we sleep our application for a few minutes and then the sleep was fast forwarded, we can use get tick count or read the tick count from kernel user shared data to validate if the tick count is bigger than before sleep for the specific value, and if not, if this analysis was fast forwarded, our delay was fast forwarded, we will get a discrepancy in tick count. So it's, for us, it's an indicator that the sleeping function was hooked, and some analysis environment fast forwarded our execution delay. So it's a good idea to terminate the application here. So that was the thing about sleeping, and now into function hooking and unhooking. So as I said in the before example, crucial system functions may be hooked by EDRs or antiviruses or any sandbox environments to monitor and combat our malicious behavior. So for example, thread creation or process creation or memory allocation functions can be hooked to intercept and investigate actions that our code is performing. So what can we do about it? We can just find those hooks in memory by loading specific functions in memory and then comparing the opcodes with assembly in the library on a disk, because when the DLL was loaded from a disk and modified by some EDR solution, the first opcodes, first instructions will be different than in the original library, because there probably will be some call to external function located in, for example, antivirus module. So we can compare the opcodes to find hooks, if there are any. We can unhook functions by overwriting those opcodes with original code. So like restore the original assembly, and that way the functions will be unhooked because they will be executed as normal. And we can try to completely bypass function hooks by issuing syscalls directly to the kernel. So here is an example of create thread function execution. When we call create thread from kernel 32, like in this shellcode injection proof of concept, several functions are called, and then anti-create thread external is called, and then this anti-create thread function is basically a wrapper to a syscall, and syscall works like this. Syscall ID is pushed to EAX register, and then the execution is switched to kernel mode by this syscall instruction. And you can see on the process monitor excerpt here that at some point execution is switched to kernel. So to avoid to bypass syscall function hooking, we could just issue those syscalls directly to the kernel. So for example, we can that's how I implemented it. We can write some simple assembly to call the issue the syscall, and then call this assembly function, but as a pointer to create anti-create thread function. So specific parameters will be passed to registers and to the stack, and then the function from anti-DLL library won't be called, but we will call the kernel directly to, for example, allocate memory for us, or here create a thread in a process for us. So it's a good technique to bypass those function hooks.
Yeah, in the previous part, we always created a new file, which really means that it actually has to force our victim to use this file. And we can also make use of an interesting already existing file of the target machine. So this is we would like to focus on an executable file, and we like to backdoor some portable executable file. And unless we are forced to use a specific binary backdooring this file, there are some points points which actually should be kept in mind. They are, however, not required to be followed, but preferred because they will help reducing the antivirus detection rate and probably making the product more visible. So first of all is try to make a look at the file size. Smaller files are easier to transfer, of course, and usually it's easier to debug them in case of issues. And it's a good idea to backdoor a well-known product, for example, a program which actually our victim uses. And using this known portable executable file is actually not required, but there are some chances that antivirus will be more inclined to execute a known program. And it's always a good idea to use a C or C++ native binaries and try to use the file that legitimate feature is using a network. Because if we use, for example, a Paint application, it probably won't be using network, and it's more likely to be detected by a blue team. So we won't be so easy cached. And the last thing is avoid using files that are not protected, using a security features such as ASLR or deep execution prevention. And let's go and verify that. So there are some techniques like ASLR and deep execution prevention, which actually prevents us from hijacking our code, like for example randomizing the memory and preventing from running other code from memory. And there's an interesting script called get PE security, which actually gives you an idea what the program has been, what the features that the program has been compiled with. And we can make a look, for example, with two different versions of a 7-zip file, one of which consists of depth protection and one not. So probably the most we will be trusting with this one that do not have this deep protection. Okay, and once we found our target, we probably would like to make some static analysis of it, and we will make use of in this case on a putty file. So putty is an interesting file because it's a native C++ project, so which uses multiple libraries and Windows APIs, and it's also a network a program that uses a network for a normal activity. So we probably won't be attracting so much attention when it comes to the network monitoring. So the blue team won't probably be so suspicious about this. And what we're gonna do, we're gonna actually inject our code. And there are two actually approaches to this portable executable file exploitation. One of which the main diverse is to add a new section in the memory, or to find an available space for a shellcode. It's called which is called a code cave. Then the flow is pretty the same. So we copy the opcodes from the stack at the beginning of the programs, then replace those instructions with our own opcodes to hijack the execution flow. Once we hijack the execution flow, we inject our shellcode, and we set the registers back. So we will allow the normal execution flow of the application. So the first one would be adding a new section. So we will be going to add a new section. In this case, I've added zipcon section. And just to remember, not only when using, for example, CFF Explorer, add a new section with the empty data in it. In case you add only a header, you need to fill the section before running the program, because it will probably crash. And once we do that, we need to change the flags on this section in order to make it executable, so we can execute our code from this section. And that's what we did. We placed an empty section which now has 0, and this one has a full permission, and we are ready to proceed. but actually proceeding is not so easy, because once we do that, probably Windows Defender and or maybe what kind of antivirus do you use will probably at the moment eat this file, because even when adding an empty section with a full permissions to an executable file, antivirus solution may consider this file as suspicious. So Defender do that, and we have a problem. Let's try what the VirusTotal says, and it says that there is really a relatively high score, and we literally didn't start it even placing our shellcode, and the file is already executed. So maybe this is already cached. So maybe it's not a great idea to follow the step. As a short summary, we can see pros and cons of this method. Of course, we can move forward with that, but the chances that we are going to make the detection rate slower are very unlikely, or not so high as the other method. So the biggest pro is that we don't need to worry about the space for our shellcode, and so this is really useful. We can also place our own encoders because there's a plenty of space. But actually, as we've seen before, adding a new section header and assigning it execution flag will most likely alert an antivirus solution. And we also increase the size of the file, not so much, but still. There's a better solution. This is called a method with a code cave. So what are the code caves? Code caves are that or empty blocks in memory of a program which can be used to inject our own code. So instead of creating a new section, we will make use of existing one. And to find an existing one in our memory, of course, we won't do it by our hand. There are a couple of scripts and tools to do that. I prefer using Cave Miner. So we can use the Cave Miner to find shellcode in our file. Cave Miner is really interesting because it also gives you an ability to check whether the inappropriate flags has been used in this file. And as we can see, the input only which we need to provide is a desired size of a shellcode. We can go then once we find an appropriate code cave, we need to check which section does it exist in, and we know there's a data section. We need to make it executable in order to work. And once we do that, we probably would like to hide behind the user action, because the way we want to run our code is to hide the execution flow straight after the user interaction, because it is not a suspicious action then. And we need to find some action. So in this example, we will probably use the main feature of a PuTTY, which is clicking open button. And once we click open button, connecting to a legitimate server, we see that string login as. So the first step would be to look for a test string references in our PE file, then place a breakpoint there, because there may be a couple of different strings in this file. Good idea is to put a breakpoints at each existing string reference, and then run the program and verify if we do the desired action and do we hit our breakpoint. And that's what we actually did. We hit the breakpoint, and this will be our injection starting point of our injection. So we actually need to do how much space do we need for our shellcode. So let's generate our payload, and as we can see, we need as much as 324 bytes for our shellcode. Let's go back to a Cave Miner. We got a couple of two different Kate codes. Let's use the second one, change the appropriate flags, and we can proceed. As we can see, the cave looks pretty nice. It's empty and it looks like a perfect place for our shellcode. But it's always a good idea to run a program and verify whether it actually changes during the program run. And it happened in this case. The program, the space got handled, and some of the instructions were changed. So we need to find another code cave which was relatively close, like 20 bytes further. So we will use this one. And we would like to hijack the program execution flow starting from this entry point, which we set previously as a breakpoint, to this empty sanction. We've done that, and we can now proceed to a placing of our shellcode in this particular code cave, which is really simple. We can use this piece of code. First, we need to save the registers, save the flags, then put our modified shellcode. Why modified, I will talk in a second. Then we need to restore the flags, restore the registers, and make a stack alignment, and that will be enough. And this little modification which we need to do is because due to the our Metasploit payload, because at the end of the shellcode we see there's an opcode called EBP, which actually terminates the execution of the program right after the shellcode is executed. We don't want to program to terminate once the shellcode is executed, so we'll like to change that to a no opcode, no operation. And because the call EBP is 2 bytes long, we actually need to use 2 no operations. And inside of it, there's another place we need to change to NOP. It's DEC Inc, which actually is a feature that once the program is running, the shellcode is running, it waits for the user input. We don't want to wait for the user input, so we need to change this DEC Inc for no op2. And once we place that inside of the code cave, we can run the program, and we can see there's a shell coming to us, lucky us, and see whether it actually was usable in this case. And well, it actually is not the perfect one. It's still high detection rate. Why detection rate is so high? Because we used a raw shellcode from a interpreter. So what we're gonna do, we're gonna use the method previously mentioned by Patryk. We use XOR encryption. Nobody and no solution will try to break our code, our encryption at this point, because it's not what is going. It's what is going in the memory, and we will like to encrypt that, and the shellcode in the code cave will look pretty the same, but just before the shellcode, we need to place our encoder and decoder, which will decode our shellcode to avoid static analysis. And decoder is right there. Decoder is relatively simple because first we need to place shellcode start address in a EBX register. Then we would like to XOR the content of the EBX register using our own key. Then increase the EBX and check whether we already reached the last address of the shellcode. And if not, jump back to our XOR command until we reach the end of the shellcode. And was it a success? Well, as we look, we can place a breakpoint just in the end of the decoder, and as we can see, the rest of the shellcode has been changed. We can now save this file as it is because encoder already encoded our payload, and once we run it again, it will work. And the detection rate is relatively slow. We managed to get 5 and a virus total, so it's a good starting point. There are a couple more options to make it really low. For example, we can chunk our shellcode into a multiple code caves, so it will be even harder to static analysis for antivirus solutions. But this is a story for a completely new presentation, and we think we can go to the last section, which is hiding imports by Patryk. Patryk, microphone. You have a muted microphone.
Thanks. So we are running out of time, so let's quickly discuss this import table and hiding function from there. So when we compile an Windows executable, when we are using some API functions or any functions from external libraries, the information is placed in import table of the executable. And one simple thing to do to bypass this is to load the functions dynamically during runtime using get process address, get module handle, or load library. So we can hide those sensitive functions like create thread, create process, allocate memory, or whatever. So only get process address function is visible in the import table, but those library loading and process locating functions are also an indicator of some malware, especially packers like UPX use those functions often. So we can take some measures to hide those imports too. And to do this, we can use the algorithm used by Shellcodes. So we are locating process environment block in memory, and then finding loader data and all modules and kernel 32 module, and browse for function addresses. So it's quite a long code snippet here. So to briefly show what's going on. In the debugger, we can see process environment block, and among other things, there is loader data and information about loaded modules. So we can locate kernel 32 address in memory, and then find in its export table get process address function and any other functions, and we then can basically load any function from memory, and that's why nothing is visible in the import table. And another thing is API hashing. So, for example, if we don't want to use function names in plain strings in the executable, which are then located in memory, we can use hashes of those names. So, for example, we can use DJB2 simple hash function and pre-calculate hashes of function names, and then just browse the exports of library and find names, hash those names, and compare hashes with our functions, and that's how we can locate needed functions. And during static analysis, an analyst won't see those function names, and we'll need to run the executable to actually find out what functions are used, or just calculate those hashes. So it's one of many ways and ideas to obfuscate the code. So that's it. You can find a lot of more of samples on my blog, and I'm trying to regularly post some new articles regarding that. I hope you found this interesting, and maybe someone would be interested in some longer workshop, because there is a material for, I think, 2 or 3 days workshop, not for a short presentation. So anyway, we try to
we hope you enjoy the rest of the conference, and I think
yes.
and I think thank you for watching us. Bye.